Good day, everybody, and welcome to this first issue of AE 3515, which is the course devoted to system dynamics. So, to begin with, I just want to tell you a few things about this course and about myself. My name is Eric Feron. I will be your professor throughout this semester. I have been a professor for about 21 years now, and I have been teaching this course virtually forever. Those of you who are linguistically oriented may have noticed my accent. It has not changed over the past 21 years. There is no chance he's going to wait and change over the next 5 months. We will now get started with the actual description of the course, and for that purpose, let me open a web page. The web page of the course can be found at the address above, feron.org. Let me change this a little bit and go to full screen. So feron.org/Eric with an uppercase E/system dynamics. The prerequisite material. Okay, so let's go further. Let's slide back up. You have the name of the course. You have when the course is offered on Monday from 2 to 3 p.m. and on Tuesday and Thursday from 12:05 to 13:25 p.m. I am not sure this is accurate, but we will do with this for now. The first meeting is at 2 anyway. The location is the Manufacturing Research and Development Center 2407, which is located near, in fact, within the Department of Mechanical Engineering. You recognize the Industrial and Systems Engineering Complex here, the Student Center about here, our school lost in the lower right corner, and the Mechanical Engineering Complex about here. And you also recognize First Drive as it loops around, leads you to some student complex here, Hunt Hill Avenue here, and then further north, North Avenue. Going back to the course, so I will be your instructor, and thus at all times. Sometimes I will not be present, but all the lectures will be recorded, and in fact will be available to you prior to the in-class meeting, which we will devote to other things. I therefore expect you to listen to the lecture before coming to class. If you don't do so, then I will not be basically helping you. My location is ESM 203A, and the grader and the TA remain to be determined. My office hours are from 3 to 4 on Monday and from 3 to 4 on Tuesday. I don't intend to change those. With all the exposure time you have with me, you have plenty of opportunity to answer all the questions you want. So the description of the course is the dynamic modeling and response of systems with mechanical, hydraulic, electrical, and or thermal elements. We'll be concentrating mostly on mechanical elements. We'll be showing the classical methods of feedback control systems design and analysis. Eventually, what I hope you will get is a foundational knowledge of dynamics and control of physical systems, and that you'll be ready to take on the following courses, which include flight dynamics, aircraft and spacecraft flight dynamics, and AE 4525, which is the feedback control system design lab. The way things will work, lecture-wise, is as follows. You will have in-class participation. You will have, let me try and make this more readable. Doesn't seem to be working that way. You will have homeworks. They count for nothing. Okay, they are your work, not my work. The in-class participation includes, on the one hand, you're asking at least one question per week. If you don't ask any question that week, then you will not be graded any better than 0. If you do have a question that was asked by somebody before you, too bad, you have to think about another one. At least that will force you to start thinking seriously about the lecture before we go about it. A good question we will describe about what it should be later during the class. But in short, it should be fully justified. It would show everything that you understand up until the question in such a way that your question is extremely precise and not anything like, I don't understand anything to anything. This is not proper. A proper question summarizes where you stand, what you get, and what you don't get. I assure you that 90% of the time, if you follow that procedure, you will actually get the answer to your question before even having to ask me. However, feel free to ask me a question whose answer you already have, as long as it's well asked, and for the purpose of sharing your experience with your comrades and classmates. I will be inspecting your notebooks at random times to see the quality of your note-taking skills. Notebooks with sparse, unreadable, insufficient, and handwritten notes will be graded lower than readable notebooks with complete information. If you have a problem taking notes, that always happens, and I know that, for example, this happens in the case of dyslexia, then I will certainly waive this requirement. The quizzes count for the total grade, basically 75%, 79%. My course letter grade policy, you see on the screen. You pass as long as you do from 45% to 100%, and that is not easy. It's the low grade passing, the low passing grades and the low honors grades are there only because I tend to grade low. I don't see why I shouldn't be able to use the full scale of the grading and cram everything between 90 and 100, cramming all the grades between D and A within the 10% range. I don't want you to use any cheat sheet during the exams. This is a change from the previous years, and the reason is because I think they're useless and they're in fact hurtful. So again, the homework is your problem. Feel free to do whatever you want with it. Eventually, you train yourself and you don't train me. So there are a few homework directions that I asked you to follow for the purpose of helping the grader who's there to serve you. and address your needs. Feel free to contact the grader if something is not clear in the indications that he or she gave you. The prerequisite material include, on the one hand, AE 2220, which is mechanics, and on the other hand, differential equations, which is the Math 3 course, if I remember well, 2403. It is very important that you understand differential equations. This course is all about differential equations and their solution. So you will use this web page to refer to anything you need, and I will update it from time to time. The book is that by Ogata, System Dynamics Principle, 4th edition. The schedule is here for indicative purposes only. Today is the introduction. Tomorrow you will see the Laplace transform for about 4 or 5 lectures. We will then talk about mechanical systems, how to describe them, how to capture them in a proper framework. And we will then move on to transfer functions. Okay, transfer functions are proper representations of dynamical systems that are exceedingly convenient, if not new to you. We will then return to a differential equation description of mechanical systems through state space systems in chapter 5, which will be followed by more mathematical analysis of all these systems. In chapter 8, we'll be talking about system analysis in the time domain. In chapter 9, we'll be talking about system analysis in the frequency domain. And then there is a repeat here. It's not, chapter 9 is not about control system analysis, my mistake. Chapter 10 is about control system analysis in the time domain. So erase this part. Okay, I refer to this part instead. Then chapter 11 will be devoted to control system analysis in the frequency domain. We will be drawing correspondences between chapter 10 and chapter 11 in such a way that you are able to understand how these two talk to each other and in fact are part of the same body of knowledge. By the end of this course, you will be probably overwhelmed, but hopefully you will be prepared to take a good second look at all this material when you take 3521 on the one hand, and especially 4525 on the other hand. Okay, when you see system dynamics here, there is notion of system to begin with, and the notion of dynamics. Okay, and we should add control. Okay, which will be the last element. Okay, so the first part of the course will be devoted to systems. Okay, and that's what I want to talk about today. All right, so if we clean that up, okay, I want to talk in general about what systems are. Okay, so systems. There are many definitions of systems. Okay, you can find them used more or less loosely in a variety of contexts, so it's important to give you the context in which I'm going to use that. Okay, so for me, a system is taken out of its environment. Okay, it must contain itself, and it must contain the way it interacts. In such a way that, provided the environment, provided with the system, okay, we shall call S, okay, and provided the interaction between the system and the environment, where the interactions may be interactions in or interactions out, I can basically describe all behaviors of the system. Okay, so without further ado, okay, I can simply pick some examples. So some examples may include, to begin with, for example, an engine. Okay, so an aircraft engine is something like this. Okay, I would say this looks more or less like a turbofan. Okay, it has inside a fan, it has a turbine, it has maybe a couple of compressors, okay, and a couple more turbines, in such a way. And by the way, it has a combustion chamber, okay, which I call C. Okay. Now, this engine has several components, and when it is considered as a system, we may look at it the following way. Okay, taken out of this environment, what does it do? Well, it has its own behavior. Okay, and its own behavior may be, for example, the speed, linear and angular, of the whole thing. Okay, then it may contain also the, hold on, it may also contain the speeds of the different elements inside the turbine. Okay, so usually there are two shafts in an engine. Okay, the first shaft acts on what's called the low pressure stage of the turbine and links the front and the back guy together. And then there is the so-called high pressure shaft, which links the compressor here, the high pressure compressor, to the high pressure turbine there. Now, in terms of speeds, they are summarized by the speeds of the two shafts, which are N1 for the low pressure shaft, and then N2 for the high pressure shaft. So taking this engine back, we can look at other variables that are of importance to it. One of them will be the thrust, okay, and that's an interaction variable with the outside world. Another one is the fuel. Okay, so the fuel flow is certainly a variable as well. Now, on the other hand, the exhaust gas is also an important variable to understand the operation of the engine. Okay, and so just like in dynamics, okay, what you see is that the definition of a system goes through the definition of all the variables of interest. Now, we can pick another example of a system. Okay, so that would be something much simpler. Okay, and as it turns out, this is something that we will study quite extensively. Imagine a system which is made of a wall, a horizontal surface, then it's made out of spring, and to the spring there is a mass that's attached to it. Okay. Then we can define the system in several ways. Okay. So one of them would be to describe the system as just the maths, like this. Okay, as it interacts with the rest of the world. In which case, what could we do? Well, we could say that the state, if this is our system, okay, so let me emphasize that for 1 second. So if this is our system, then the number of variables we need to describe this system include the position of the system, the speed, and then probably the force that acts on it. Okay, and that force could be A, the force acted on by the spring on the mass, okay, and second, the force that the ground does on the mass as well. Okay, so let me summarize these forces. And I think that once this is done, this is pretty much everything that needs to be done. Okay, in order to sort of capture this mass. We may have forgotten one thing, which is to describe the mass itself, that is how heavy it is. Okay, we may need also a few other characteristics, such as the friction coefficient mu that links the mass together with the ground. Now, another system we could describe is as follows. Okay, it is the same mass spring system. Okay, however, now what we do is we include the spring as part of the system. Okay, so how would that look like? That would look like defining the system as this thing. Okay, and then so if we define the system as this, okay, then things change a little bit. Okay, in a sense that we still need position and speed, but the forces in absolute. Okay, we still have the force that links the mass to the spring, but we also need the force that links the spring to the wall. Okay, so that force there. Okay, and so that would define our system a little bit differently on top than what it is at the bottom. Now, some of the systems that we are interested in can be enormously complex. They can be made of several components. A typical example would be an aircraft. I'm going to try and draw this here. An aircraft, let me change color, would include as many things as fuselage, wings, engines, and many control surfaces. And then for such large systems, and of course the avionics. Okay, very important. And the pilots. Okay, and for these very complicated systems, it may actually be beneficial to first describe each element of the aircraft separately. In which case, each of these elements described separately are subsystems. And one of the great positives of the systems approach, okay, as we will see in this course, is the modularity. Let me try that again. I said modularity. What does that mean? That means that a complex system will make by describing a bunch of small subsystems, okay, and then maybe describe how each subsystem interacts with the other, adding on top of which all the additional interactions with the outside world. And the interactions maybe out or in. Okay. The net results of this is that what you will see very often in the dynamical systems that we're interested in are these so-called block diagrams. And those block diagrams are really a description of how each subsystem talks with each other, okay, by having the nature of the interaction between each subsystems, the nature of the interaction with the rest of the world, and I forgot to add the interaction of the system with itself. Okay, so the system variables that describe the internal state of S1, S2, S3, and S4. Okay, but again, these are internal variables. Okay, so now what I want to add is that we are talking about dynamical systems. So what's a dynamical system? Okay, so a dynamical system is a system for which time counts. Okay, so we have a clock that ticks, okay, and gives us the time t, and we consider time t to be very important. In the context of the examples we have here, and those we will see in the book, we assume t is universal, and we assume classical mechanics, as opposed to, for example, Einstein's relativity. Okay? And what does the presence of time tell us? It tells us that every one of the systems that we're going to study is going to be evolving with time. Okay? And when you think about it, there are all sorts of evolutions that we could be thinking about. Okay? So the kind of evolutions that we could be thinking about are possibly discrete. For example, it works it's broken. Okay? So that would be one state, that would be a second state, and of course we go from the first to the second state by having at some point a transition from it works to it's broken. And of course once it's broken, it stays broken. Okay? This is more or less a sort of detailed way of how computers work. However, what we have is more than just a few simple discrete states, like it works, is broken, but we have the states of all the bits of memory which are at 1 or 0. Okay? And so what that means is that these discrete states are pervasive in computer systems, and we will look at them, but not as much as systems which evolve in continuous states. Okay, so what's that? A continuous state is a case where instead of being discrete, say it works, it doesn't work, the system evolves continuously. So typically physical systems. So for example, if we take again the mass spring system that we discussed earlier, okay, this system will evolve continuously that is speed and position are smooth functions of time. Okay, so since they are smooth functions of time, what that means is that we can represent them, for example, as follows. Okay, position may look like this. And if that is the case, then the speed is likely to look like that. Basically be a little bit out of phase with the position. Okay, and these signals are smooth. Okay, they don't correspond to abrupt translation, or at least we cannot see them in anything else than via via continuous transitions, both say here in position and here in speed. Of course, that axis is time. Okay, and what we will see is that in that context, differential equations are very important. Very, very important. So if you didn't score well in DFQ, you should pay attention and try and remember as much of it as you can, because we will be using them. Okay, extensively. There will be things of the kind x dot equals f of x comma t comma maybe some input u. Okay, like an interaction variable. Okay, all right, so let me add something now about the nature of the dynamical system we're going to see. Okay, so what we're going to see is mechanical systems. Okay, we're also going to be seeing electrical systems. For example, the capacitor resistor system here. Okay, so let me remind you, this is mechanical, this is electrical. We also are going to see computer programs. So these will also count as subsystems, and under particular conditions, we will see that we can represent them as differential equations. Okay. There are many other systems that we can consider. For example, fluid systems like dashpots and things like that. We will cover them on an as-needed basis. Okay. All right. Now I have covered this. Okay. Let me go back to these differential equations. Okay. So what we will see is the following. So differential equations come in all shapes. And all level of complexity. So because of that, we will have we might encounter like great difficulties in solving them. Okay, we could have like partial differential equations, which are the most horrible of all, but we will limit ourselves to not PDEs, but in fact ODEs. X dot equals of f times of x comma u comma t. Okay, we will represent our systems this way, and in fact we will sometimes simplify this to get linear ODEs. X dot equals a times x plus b times u. Okay, and there will be no explicit dependence of time. Okay, so what that does to us is that it will de facto simplify our analysis without necessarily sacrificing the quality of the analysis, but it will provide us with a ton of super powerful tools to analyze our systems. And this is why we will be relying on them. The reason, therefore, why we will be focusing on linear systems is because they are powerful enough for us to explain many things. What will we encounter in the near future? Well, questions such as how do we represent a system as ODE or even linear ODE. Okay, so that's the first step. Okay, and it's a modeling step. The second step is how do we understand system behavior? And this is where the Laplace transform and the state space analysis are very important. Okay. Last, we'll be looking at how do we change the system's behavior. And this is where we will be interested in controls and control techniques. This science is a little bit bizarre. It is somewhat difficult, but by the words of your predecessors, is the closest thing that, or it's not the closest, the best thing to link math to reality. Now we will see that later, but I just want you to give you this motivation, even though you will see that only in 4525. Thank you very much. Have a good day.